Max, you still there?
Yeah.
Ah, there's one thing I forgot to tell you, and that is, can you see the panelists panel? If you press on panelists.
Just 1 second. I just
Oh,
lost.
yeah. Sorry, we're live. Everybody's listening to us right now. All right. Let's. I'll tell you later.
Okay.
Yeah, good morning, everybody. Good afternoon, good evening. Welcome to today's EMinar. Should be a really exciting one. Max is going to tell us some wonderful things about his models and interpretations there from some large data set. So today we have Max Moorkamp on distinguishing melting fluids from graphite in the lower crust with multiphysics inversion. And I can see we already have 76 people in. That's great. So tomorrow, next week, we have Karen Whitemeyer on autonomous underwater vehicle-based electrical magnetic fields. She will talk at 1600 UT, so a couple hours later than this. And then we have Xavi Garcia on fundamentals of time series analysis. So Xavi is one of these educational seminars. He's going to give us a whole background on the basics of time series analysis for transfer function estimation. And then a few weeks later, we'll have Alan Chave on some more advanced things. And then we have Ken Witherley. Ken's in industry, been running a company now for a few years, and he's going to talk about an exploration model, copper porphyries, and the role MT has done a great job in a lot of places, and he's going to explain to us just how MT has been useful in the copper porphyry exploration model. But it's also going to talk more in an educational, but also in a career sense. He's going to talk a little bit about his career in industry over 40 years. And then the final one before Christmas, the Christmas break, is Hao Dong, who's going to talk to us about this wonderful program in China called Sinoprobe. So please go to the webinars page and you'll see the list of upcoming webinars. And then those that are ready to join, you just have to press on the registration link. And then those that are, just hang on a minute. Is this? I'm not seeing the recording light. It should be oh, it is recording, right? Just checking it's recording. Okay, and those that have previously been recorded, you've got a video link, and in some cases you'll get a PDF of the presentation. So yeah, please come back regularly because these things change. And for example, we've just added in a special event coming up on the, depending where you live, it's either the 10th in North America or it's the 11th in Europe and Asia. And this is a joint event with the British Columbia Geophysical Society. And it's actually a discussion. We're going to have 4 of the top people in the world who do time domain electromagnetics who are going to discuss this topic of on-time step response and low frequency B field. So this will be very interesting. And we don't have that set up as a registration, but you can click on the information link there. And finally, you're in a webinar right now, so you don't have the same tools that you have in a normal Zoom meeting. You'll have a bar like this, and you have your audio settings. You have a chat function, and that sends a message to the panel or participants. You can raise your hand if you want to be noticed. And then at the end or at any time, you can introduce a question. So there's press on the question and answer, and you can write questions in at any time. And Max, if he glances at these, he might be able to answer them on the fly, or we'll answer them at the end. Okay, then with more ado, I'll just stop sharing and hand over to Max Moorkamp.
Yes, thank you, Alan, and welcome everybody, and thank you for attending this webinar. Can somebody confirm that you can see my screen?
Yep.
Okay. Yeah. So when Alan contacted me about sort of setting up this webinar, one of the first things I said to him was, yeah, we should make sure that we don't hog this thing too much and sort of just present our own stuff. And then virtually the next thing I said, but I really want to present something as soon as possible. So apologies for that, but I'm quite excited about these results, and I really want to sort of show them and also get feedback on them. I expect that there will be some people here that find these controversial, and really I want to hear your thoughts and your criticism. So I'm going to talk about the, well, fairly old problem that we have in EM of how can we distinguish melts or fluids from graphites in the lower crust. And I'm going to show you how I think I have found a way that can help or maybe can solve this with multiphysics inversion or joint inversion. So I'll start with a bit of background into why this is an exciting problem and sort of some of the historical context, also for those of you who are maybe sort of new to MT. I will then explain our new joint inversion approach and what we do there and how it helps sort of solving this problem. And then I'll show you some data from the Western US, some application there to the US array data, and how I interpret these results in terms of melt fluids or graphite in different parts of the Western US. So from the very beginning, virtually, when people started doing MT in the 50s and 60s, the results they got suggested, or they inferred from those results, a high conductivity structure in the continental crust in many areas, mostly in sort of younger areas. So the cratons seem to be more resistive, but in many places they found conductive structures in the lower crust in depths between 20 and say 40 kilometers. And one of the first models that was developed based on this was published by Hindman and Hindman in 1968. And they suggested fluids as a cause of this high conductivity in the lower crust. And here on the left-hand side is one of the figures from this original publication. And this was published, mind you, in 1968. So this was just around the time when plate tectonics was starting to get established. I think 50 years of plate tectonics was celebrated in 2016 or so. And if you look at this and the nomenclature here, you can see on the top left, so this is basically the starting point where they say, okay, we see sort of a resistive structure at the top, and then it becomes more conductive as we move down to the base of the crust. And they call this a young geosyncline. So this is clearly pre-plate tectonics sort of conceptual model where things can't move laterally but only move up and down. And I think in this paper, or one of the papers he cites, they even write basically everything is to some degree metamorphous sediments that have just been sort of piled up from the top. And the idea here is that while this is sort of young, you have fluids down at the base of the crust, maybe also some of them coming from the mantle. And then as it gets older, these fluids move up, and you get less of a conductivity. And then when you move into cratonic areas that are really old and have been around for a long time, then all these fluids have been removed and you get this sort of only mild conductivity increase. And of course, from a modern viewpoint, this is outdated. Yes, we think about processes within the Earth quite differently now. And for me, especially considering the publication date, this is always a bit of a reminder, or if you want, so a bit of sort of humble pie to eat about our own sort of inferences and interpretations of our models. What will people in 50 years think about those, and what we thought was going on. But so that's how it started. But one thing I wanted to show here and quote here, which I found in sort of one of the papers that was cited, and this was one of Ulrich Schmucker's first investigations in the Western US, and the models he found. And he writes in his paper, it might be added that the only...
Sorry, Mark, sorry, just to jump in. You've got a lot of screens on the side there. The Zoom chat, the participants, and question and answer.
Yeah, I wanted to make sure that I can see the questions and answers. I didn't know that you will see those as well. Better now?
Okay, they're gone now, thanks.
So he says, it might be added that the only deep anomaly which could explain the anomalous variations along the coast, and he's talking about the sort of California coast there, would consist of a step in the surface of the conductive core of enormous dimensions. And you can hear from his tone that he thinks that this is all a bit ludicrous. On the oceanic side, the depth of the core would not be greater than about 20 kilometers. On the continental side, the depth of the core would range between 80 and 250 kilometers, depending on the period. And this was written in 1964. So again, plate tectonics, and at least I read this tone that he thinks that this is all a bit sort of implausible and quite impossible. But of course, with a modern view on these things, you could argue that, okay, maybe 20 kilometers, he was seeing oceanic crust and sort of some signature of transition to melts there. And he was seeing the continental LAB at 80 to 250 kilometers. So, maybe as a bit of contrast to what I said previously about the Hyndman and Hyndman paper, yes, our measurements, it seems at least, do have something in it. We might not always understand what that is until a lot later. But back to sort of conductivity of the crust and some sort of more modern examples. So we've moved on quite a bit since then, but we still see these phenomena all around the world. Here's an example from Ireland, where we made some measurements across the Yapata zone, and I think CK is in the audience. So CK Rao was the main lead on these inversions. And I sort of participated in the measurements there. And you can see here one of those typical examples that we see in a lot of models. We have high conductivity between 20 and 30 kilometers with quite a bit of variability in depths. We see sort of correlation with some of the faults here. And here, one of the interpretation is that at least some of this conductivity is caused by graphites or sulfides in some metamorphosed sediments that then have been deformed and sheared and caused this high conductivity and also caused these changes in depth and all this structural variability. Another example, also very famous, and many people have worked there, is Tibet. Yes, here's our horizontal slices through a recently published model by Dong et al. From 10 to 35 kilometers, and you can see the 10-kilometer slice on the left. We have quite high resistivity, and by 35 kilometers, we have reached quite substantial sort of conductive structures. And here they interpret these structures as fluids or melt associated with the ongoing tectonic activity, and sort of indicated also by high heat flow. And this is by far not the only study that sees this since the 90s, when the first sort of MT papers in this region, at least that I'm aware of, came out. People have invoked these kind of explanations for high conductivity. And then finally, because we're going to move there sort of in the next step anyway, when I show my results, some results from McBell et al. For the Western US. Here now a vertical slice across the Western US in, I think it's sort of Oregon over to Wyoming and sort of across Yellowstone. The white dashed line is the moho, and we can see here extensive conductive structures at the bottom of the crust and maybe in the top of the mantle. And again, because this is an active region, yes, Yellowstone sits here sort of at the boundary to the Wyoming Basin. A plume is suspected. The interpretation is that this is fluids and or melt, and they are associated with the ongoing deformation in the Basin and Range, and probably associated also with the plume. So if you want to summarize the modern explanation for high conductivity is that we have some sort of small amount of a connected conductive phase, 1 to 10%, maybe a bit lower in some cases, maybe a bit higher in some resistive host rock. These can be either highly hypersaline fluids, and we need to invoke some mechanisms that they are retained in the crust. And sometimes you see those invoked also in combination with melt, for example, in Tibet, but also in the Western US. And melt is another explanation. Of course, we need a lot of heat to that we can confidently say, that we have melt at sort of 15 or 20 kilometers. So usually that's restricted to very active area. Graphite, I showed the example of Ireland, but this is also invoked in other areas. It's typically seen as a remnant of some past activity, either some fluid movement that can move graphite through the crust or some sort of deformation. And sulfides, which at least I think at the moment seem to be less favored. I see less publications that invoke these, maybe because they're thought not to be so abundant. And typically, which one of those is invoked is based on, let's say, the tectonic regime that the study is thought to be in. So the active areas, as I said before, are typically fluid melt. More old areas are graphite and sulfides. And the problem here is that with the ranges, let's say, of fluid, melt, or graphite that we expect to see in the crust, we can't really, or they produce the same conductivity range, strongly overlapping, so we can't really distinguish with MT, unless we would know, for example, the fraction of material that we expect to down there. So that's why we haven't been really able to sort of move forward on this from a purely sort of data perspective. But as I will hopefully show you later on, these materials have quite a different density. Yes, so fluids, for example, would have quite a strong density contrast with the surrounding materials, whereas graphite and sulfide have virtually the same density as the host rock, and then melt is somewhere in between. So that's where the joint inversion comes into play. And we will be looking at the US array data from the Western US, so very similar to the extent that McBell et al. Have been looking at. I mean, this is an excellent data set, a great resource that can be used. As a reminder, I'm just putting out what can be downloaded from the IRIS website at the moment, and I think Paul Bedrosian is going to give a talk in a few weeks' time. I'm not exactly sure about the date, so you can look that up on the EMinar webpage. And we will focus here on these yellow sites over to the west. You can see that not all the US array sites have been included. This is because I only selected the high quality data. So there are some stations that have some data issues, and those have been excluded from the study. But overall, we have a sort of extremely high quality data set in a wide period band. And I will combine this with satellite gravity data from the XGM 2016 combined gravity model. But before I go to the results, I need to explain to you how we go about the joint inversion and the new aspects that sort of allow us to make these inferences. So this is, if you want, so the briefest primer on joint inversion possible. There are different review papers, and I had a review talk at the MT induction workshop a few years ago, and there's a paper associated to that. So if you want to know more, please look at those. So this is, yeah, the briefest possible summary. So the idea of joint inversion, or multi-physics inversion, as it's called sometimes, is that we combine different types of data set in a single inversion, and we create a consistent model between those different data sets that improves the information content in some way. And I leave this sort of intentionally vague because yes, there can be a sort of whole discussion to be had around that. So here we have magnetotellurics that's sensitive to conductivity, and gravity data that's sensitive to density. And in the inversion, we set up an objective function and a quantity that we want to minimize. And for our joint inversion, this has a slightly simplified version 3 terms. We have the data misfit for our MT data. And so this is how well our model predicts or matches the observed MT data in the region. And that only depends on the conductivity. We have the same term for the gravity data, so the mismatch between gravity observations and those calculated from the model, and that only depends on density. And then we have this crucial thing that makes it a joint inversion. Without this, we wouldn't actually have a proper joint inversion, and that's this coupling term that defines what are our assumptions about the connection between density and conductivity. And within the inversion, we then try to minimize those 3 terms. So we want to make the data fit for both data sets, and we want to have a good coupling. That means a minimal sort of coupling term between those data. In reality, there are a few more terms associated with regularization and so on, but for simplicity, I skip over this. And as I said, the coupling is crucial and defines how we expect to see this connection. And again, I'm not going to review the plethora of sort of current coupling approaches because that would go too far. We can discuss this in the questions and answers at the end, but we'll focus on what we are doing and how that works. So we're using a concept called mutual information for our coupling, and this has been sort of floated in the community for a while already. Eldad Haber is the first person that I remember talking about this sort of years ago. To use it for joint inversion, but for some reasons, this has never sort of fully taken off. And as far as I'm aware, this is the first time somebody does really sort of a full simultaneous joint inversion using this. And why is it so attractive, or what makes it so interesting? So first of all, this mutual information is a measure of information content that one variable contains about another. So variable X contains about variable Y. So it asks the question, if I know conductivity, how well do I know density? And it has this definition where you take the so-called Shannon entropy of each of the individual variables and subtract the joint Shannon entropy. And you can see the equation for Shannon entropy here, where P is the probability density function for each of those variables. Now I will give some examples in the next couple of slides that sort of make this much more clear than these equations. So for the moment, I'm not going to sort of go into that much deeper. Again, at the end, if you have questions, I'm happy to answer. And the idea is that we maximize the mutual information content as part of the inversion. So what does this mean in a more sort of visible way? So here we have 2 slices, vertical slices through individually generated models for the Western US. So this is very similar to the McBell et al. Slice. On top, we have the individual gravity inversion. And this is the typical picture you get when you throw gravity data in a smooth 3D inversion. Virtually all the structures are located at the top. You can see that especially here in the middle part at around minus 114 degrees longitude. And then through the smoothness regularization that we typically employ, everything gets smoothed down to depth, but we don't really have any depth resolution. In contrast, here we have the MT model at the bottom, and yellow here is conductive structures. Blue to green are resistive structures. We can see quite a bit of structure in the model. We can already see conductors in the crust, these yellow blobs here, and then we can also see variations with depth. So visually, these models have not very much in common. So how do we calculate the mutual information from these two models, or of these two models? What we would do is, for each cell, we take the density and the conductivity that corresponds to the same cell and make a cross plot. So that's what I've done here on the left-hand side. So we can see this parameter plot for those two models: density anomaly on the x-axis and resistivity on the y-axis. And as expected, there is no clear relationship. Knowing that the density in a certain part of the model is 0, or the density anomaly is 0, means that the resistivity can vary between 1 and 10 to the 5, so can be anything. Sort of vice versa, knowing resistivity, you have no idea what the density anomaly could be. So to calculate mutual information, we would turn this into a histogram, and this is then an approximation of the probability density function. So on the right-hand side, we have this histogram. It sort of cleans up a few things in the sense that we can see that there is a concentration of points here in the middle, and to the sides, it's actually the amount of samples that have this relationship is very low. But still, this histogram shows us knowing density gives us no information about resistivity. So this would then result, when you stick this into the equations for mutual information, and this is actually quite straightforward when you sort of think it through a bit, you get a very low mutual information. We don't know anything. Knowing one variable doesn't tell you anything about the other variable. In contrast, if we have something like this, so on the left-hand side, we now have a parameter plot, and we can see, that there is, if you want, so a hint of a connection between those two. Yes, there is a bit of structure here. It's complex, but knowing the density, the resistivity is not cannot vary across the whole parameter range anymore. We can then again construct the corresponding histogram we can see here on the right-hand side, and there it becomes even more visible that we have something like, it looks like a linear trend here in log resistivity with density anomaly. And if we calculate now the mutual information from this histogram, we get a higher mutual information. And this is what we try to achieve in the inversion. So we try to push, if you want, so that's probably the best visual way to think about it, this histogram into some sort of narrow shape, where the shape itself is not really predefined. So this can have sort of much more complicated shape. It can be disjoint, but as long as it is sort of confined in one axis at least, it means that we get a higher mutual information. So we're trying to, if you want, so reconstruct the unknown parameter relationship between those two parameters. So that's the idea of the joint inversion. Now I will show you the results for the US array, and I'll start with some background to the inversion itself. So here is the convergence of the different terms as a function of iteration. So here is the MT misfit term, the gravity misfit term, then the mutual information and the model roughness. We start with a homogeneous half space, so RMS of more than 50, quite high, and we can see how it drops down sharply very quickly. and then stabilizes at a sort of fairly low value at around 2. Here, when it jumps up again, I did two things. I changed a bit the errors, the error weighting, and also introduced more data, more frequencies into the inversion, just to push it really to the best possible model I could get for this region. For the gravity data, we can see it sort of continuously descends and then also stabilizes, but the mutual information really shows some complex patterns. It goes up and then goes down again. And this is, if you want, so this interplay between fitting the data and finding a model that adheres to this mutual information. From these plots, we can already see one disadvantage of this approach. You will see that I've been running this for more than 2,000 iterations. So the convergence, certainly to something that has both good data misfit and good mutual information, is very slow, and that's because this mutual information is quite non-linear. And so it takes quite a while to converge to a good model, but this is also partially due to the fact probably that this is one of the first times I'm doing this, so I don't have full experience yet what are sort of optimal parameters and so on. So there's still a bit of experimentation there. But certainly what we have now is a model that fits both the MT and gravity data well, and I'll show you some example in a second, and has sort of a good mutual information between those two quantities. So here is just one example. I have much more at the end of data fit for randomly picked sites. So this is quite representative of the fits we have to the data. So you can see on the left-hand side, the off-diagonal components, apparent resistivity on top and phase at the bottom, are fit well for nearly the whole period range up to about sort of 5,000 to 6,000 seconds. Then we get some divergence, certainly from the phases, but also the data becomes lower quality. And we have a reasonable fit also to the diagonal elements, both apparent resistivity and phase here, even through the whole period range. And as I said, this is representative. I'm happy to discuss this more at the end. I have more plots of the other sites and overviews. But for the moment, I hope this gives you at least some sort of confidence that this model fits the data, as well as we would expect. So with that, I want to move on to the results. So here is the resistivity plot. So we have 4 horizontal plots at different depths from 30 kilometers, then 50 kilometers, 100 kilometers, and 190 kilometers. So the coastline is here over in the west. You can see these black lines. You can probably see them best at this 190 kilometer plots because it's less busy. Those are the physiogeographic provinces in the western US. And the good thing for keeping your orientation is this sort of banana-shaped feature here. That's the Snake River Plain. So Yellowstone sits sort of a little bit away on the other side of that. And this looks, at least in overall strokes, quite similar, for example, to the results of McBell et al. We see sort of conductive structures in the lower crust, then a bit more resistivity at depth, and then sort of the resistive Wyoming craton and some other structures here at sort of higher depth. I will discuss those a bit more in a minute, but before I do that, I want to then flip over to the density model, and I will sort of flip back and forth between those a couple of times. And what you should notice, and this is particularly visible, for example, again at the 190 kilometers, where it's a little bit less busy, you can see that there's nearly a one-to-one correspondence between the density and the resistivity model, in the sense that each resistivity has been assigned sort of a certain density. And this is what we wanted to achieve with this mutual information. So for example, here we see a high density structure, yes, 100 kilograms per cubic meter positive density anomaly associated with a resistor. And here we have a conductor that's associated with a less dense structure. But you will also see that this doesn't work everywhere. For example, if you look here into the Western Snake River Plain, you can see we have a transition between low density material and high density material, but we have highly conductive material throughout, sort of across this boundary. And I will just sort of focus on this a little bit more. Before we go to this, this is sort of, if you want, so a summary slide of these horizontal slices. Again, for comparison, at 30 and at 100 kilometers. And I mean, there is a lot of information in here. I've only sort of started to scratch the surface. For example, we can see very well the downgoing slab. Here I marked this. This is a resistive high density structure, as you would expect. And this dashed line is the predicted boundary of the slab at a depth of 100 kilometers from the geodynamic slab to zero model. So this is completely independent information, and you can see how nicely we can see the shape of this slab. And for example, I think in the McBell model, they see also some resistive feature here, but it is much more spread out, particularly sort of towards the coast. Another feature we can see very nicely, and again, sort of with sort of sharper boundaries than I think previous models have done, is this so-called Silesia slab curtain. This has been seen by the seismologists, and they think this is a remnant of a previous slab that sort of went down here in one of the previous episodes of subduction. And again, our geometry matches very well with those, and also we can see very nicely the sort of transition between the Basin and Range here and then the Wyoming Craton area. So by comparing these sort of known structures, I think I hope I have instilled some sort of trust into the model as a general, so that now I can move on to sort of some of the interpretation. So we're now going to look at a vertical slice that's marked around here, and it goes sort of through the area of Yellowstone and passes sort of a whole bunch of structures. And I will also mark in this next plot the location of this, where this physiogeographic regions sort of intersect with my profile. So this is what we have here. So this is again, so the same models in a vertical view. We have density anomaly on top, resistivity at the bottom. The triangles, those are those boundaries of those physiogeographic provinces that I was talking about. The thick line here over in the west, that's the slab to zero model. So again, we can see how nicely the top of this structure sort of matches, at least in around -122 longitude, matches the prediction from the slab model, and how we actually see this as a, if you want, so discrete slab. And then these two horizontal lines are the MOHO here at the top and a seismic discontinuity that the seismologists think are the LAB over here in the west, and then a mid-lithospheric discontinuity to the east. But I really want to focus on the structures here around the MOHO, yes, the conductors in the crust. And you can see here, for example, at around -112 degrees longitude, we have this continuous conductive structure. So one of those typical, lower crustal conductors here may be going into the mantle. And if you look at the density, then we can see that to the west, this is associated with high density, and to the east, this is associated with low density. And the boundary really matches this physiogeographic province boundary. Now, this is something that clearly violates, if you want so, this minimization of mutual information. So if we want to have the best mutual information between those models, the inversion would want to assign a single density value associated with that conductivity. So the fact that we have high density here means that the data, actually the gravity data, mandates here that this cannot be, and we need to put something in there. And we can see this in a couple of other places, and I will sort of zoom in a little bit to those models so we can see it better. So here is what I was talking about before. Then we can see here in the central part, for the most part, we have conductor equals low density. But then again, moving further to the west, this flips to conductor corresponding to high density. As I said, if the mutual information constraint had its way, this wouldn't happen, and it would all be associated with the same density. So we can look at this as a sort of parameter relationship plot. So this is similar to the plots I've shown you in the beginning. We're plotting density on the x-axis and the corresponding resistivity on the y-axis. And in addition, I have color-coded the depth range from which these samples come. So we have 0 to 10 kilometers, the near surface, where I think we have virtually no resolution, certainly not sort of a coherent model. Then 10 to 35 kilometers, the crust, and then going down into the lithospheric mantle in 2 steps, and then down to the asthenosphere. And so this has come out of the inversion without any, if you want, so prior information on the shape of this thing. To me, it looks a bit like a dinosaur. Yes, you have the sort of tail here at low density, high or low resistivity, then the spine going up and a head here and 2 legs, you know, a bit like a brontosaurus or something like that. And it, yeah, and if the mutual information could sort of work as sort of undisturbed by the data, it would try to condense everything along this line. But we do see that we have some offshoots here. And just sort of looking at those a bit qualitatively, it actually makes a lot of sense. So this main branch here, yes, we see increasing conductivity decreases the density. So this suggests that whatever causes the conductivity, the enhanced conductivity, has lower density than the surrounding material. So something like a fluid or a melt. And depending on the density contrast, yes, you would get slightly different shapes of this. But then we also have this front leg here. And we can see that this is, well, close to neutral density, maybe sort of slightly higher density. And whatever enhances the conductivity for these structures has no effect on the density. So it means that whatever enhances the conductivity must have a similar density to the host rock, certainly something that cannot be distinguished within the inversion. And we can sort of refine this a little bit more. So now I'm focusing on the crustal part of this relationship. So I'm only plotting the points that are between 15 and 35 kilometers. You can see that some of this sort of near surface scatter has cleaned up, but a lot of it has remained. And these different branches, so this main backbone relationship, if you want to, and this front leg have stayed. We can still see those. So to me, this suggests that here we have something like a solid, graphite or sulfides, that have very similar densities to the surrounding host rocks. And the more we have, it doesn't really impact on density. Whereas here, this is caused by the fluids. So the spine of this dinosaur is a representation of the fluid relationship. And as a sort of extremely crude zeroth order petrological analysis, I have now drawn in the upper and lower Hutchins-Strickman bounds and Archie's law based on a fluid with a conductivity of 50 Siemens per meters, which seems to be sort of the bulk standard value in the literature, and a density contrast of 2000 kilograms per cubic meter, so something like a saline fluid. And the numbers here, those are different fluid fractions, so 0.1%, 0.3%, 1%, 3%, and 10%. And we can see that the Hutchins-Strickman bounds sort of, for the most part at least, limit what we can see here, or the range of resistivity. So, in terms of, if you want, so an order of magnitude argument, without going too much into the details, this seems to indicate that it's sort of relatively reasonable. And actually, quite surprisingly, this Archie's relationship, yes, which I just sort of tentatively put on there with, again, standard parameters, sort of even, again, zeroth order sort of matches what we see here. And obviously, Archie's law is probably in its normal form not even applicable to this. So this is not meant to be like an exhaustive petrological analysis, but more like, okay, it is plausible and we see similar things if we assume that fluids are the underlying cause for this backbone relationship. Then some petrological relationship give us sort of order of magnitude correct estimates that make this all reasonable, whereas this front leg clearly falls out of this and must be caused by something else. So now we can map this back into our model. So in this plot, I have marked the conductive structure at the bottom of the crust and made them red if they correspond to low density, and blue if they correspond to high density. And we can see a sort of a much more complex pattern than you would expect if you would just say, okay, whatever is sort of not so tectonically active, like Wyoming Craton, for example, we would just see the high density conductors, so something like graphite, sulfides, so everything up here should be blue, and here in the Basin and Range around Yellowstone, everything should be red. But there is actually a much more complex pattern. We see some, at least, correlation, as I also showed in those vertical profiles, with those physiogeographic boundaries. And for example, around Yellowstone, as one would expect, it is red, so sort of some melt induced, but very close to it, yes, and distances where you wouldn't say that the tectonic regimes has sort of completely changed. We already see that this is associated with high density. So I don't have sort of an answer yet, and I'm very curious to hear ideas, why the pattern is the way it looks. I've looked at things like heat flow and other parameters, and there's no clear explanation. But to me, certainly this indicates that this, if you want, so simple active equal fluid or melt, and passive equal graphite or sulfide interpretation is not really applicable, and we need to think about these processes in a sort of new way, in a different way, to get to the bottom of why do we see these patterns like this. And with that, I come to my conclusion. So we have this new joint inversion with a mutual information coupling constraint. The US array data, MT and gravity, gives us very detailed models, and I've only focused on the this crustal conductivity here, but there are many more features that I've looked at, and they are sort of really exciting, I find. We get this not previously specified, but quite clear density conductivity relationship, and we can relate this to tectonic features, as I've seen, as I've shown in the previous slide. And to me, this suggests, that we need to think new about this interpretation. How do we deal with these crustal conductors? What do they mean? How do they form? And how can we relate them to tectonic activity and make robust interpretations? And with that, yes, I'd like to thank you for your attention, and I'm eager to hear your thoughts, questions, and comments.
Well, thanks very much, Max. I'm sure you've got 105 people clapping very hard right now. That was a wonderful talk, absolutely wonderful. At the moment, we have one open question. Can you see that if you look at questions? From
yes,
Juan
okay. So
Basco
is
yeah, when it's an open question, the audience can't see that, so you have to read it out.
Okay. So first question, Juan Bascoa, I'm sorry if I butcher names, about US array joint inversions. What are the differences in resistivity between single MT inversion and the joint MT gravity inversion? Have the gravity data any effect on the resistivity results? Yes, they do. Sorry, I don't have that plot here, but they do. Now the MT model looks very similar to the individual MT model. So the density inversion, or the density part of the inversion, changes much more, but there is feedback the other way. And you can certainly see this in this Juan de Fuca's lab here. So if I do my individual inversion, this sort of blurs out a lot more, which is partially due to this coupling, but also due to the gravity data. So there is feedback between the two models. Okay, then next question by Matthew Comeau. Actually, two questions. So how different are the models at 500 and 2000 iterations? They are different, but the differences are actually quite small. I mean, I'm still learning how to, for example, deal with this mutual information constraint. You can see that the value range is not particularly large here, but there are, of course, differences in the details, but really the large scale features are extremely similar. And at the moment, I mean, a reason I'm pushing this so far is just to make sure that I have, if you want, so the absolute best numbers, absolute best models. And then you mentioned the Archie's law plot used fluid with conductivity of 50 Siemens per meter. I think most literature shows values less than 5 are more likely. How does that change the parameter plot? So a much more resistive fluid. Now, yeah, the couple of papers that I saw, I think including one of Alan's, quoted 50 Siemens per meter, but so 5 Siemens per meter obviously would make this whole thing a lot more resistive. So this sort of converges down to sort of pure fluid at some point. So this would shift this curve up. I'm sorry, this is not what I wanted to do. Would shift this curve upwards. But I mean, this Archie thing really, it's sort of a back of the envelope. Do we get something that's even sort of in the right ballpark? Precise, yes. I mean, Archie is pure sandstone, which we definitely don't have in the lower crust. So I wouldn't push this further than that. And if I want to sort of make a petrological interpretation, would have to think about something different, more refined.
Just a quick comment, Max, that we often see very high salinities in Archean fluids in cratons. So 50 Siemens per meter is not unusual.
Yeah, that was my impression as well. And yeah. I mean, I think if I make it 100, yes, it sort of matches a bit better this part here. But yeah, I didn't want to play around with this too much because yeah, we're only talking about, okay, are we somewhere right? Next question. So can you tell us more specifics on how you get the parameter plot between conductivity and density that seems to have formed your prior? So I assume you're talking about this parameter plot, and I think the important thing to note here is that there hasn't been a prior. Yes, the mutual information says construct anything, and this could be a plot, for example, where high resistivity corresponds to low density, so the complete opposite of this, as long as it has some sort of, if you want, so generalized functional form. I mean, you can see, for example, maybe in the previous one it becomes even more visible, not quite. So for example, I think these gaps here develop because we have this part down here. So it wants to make it, if you want, so unique. It wants to avoid that there are various possible conductive or resistivity values that correspond to a single density as much as possible. But we don't specify anything a priori. So we start with 100 ohmmeter half space and 0 density. So actually you can see some of this is still related to the starting model here in the beginning. And if I would plot this for the starting model, it would just be a single dot here in the middle. And then it spreads out, and all this is driven by the data and this tendency to form these functional relationships. Then the next question, given the differences in resolution of the methods, is it reasonable to expect that they would have high mutual information? Actually, yes. And I mean, if you think about it to the extreme, if gravity data had no resolution at all, yes, it could do whatever it wanted, then it would be very easy for the mutual information, because all it would do, it would take resistivity and assign any sort of each resistivity an arbitrary density, yes, and it would make some sort of straight line or something like that. So actually the fact that we have, if you want, so violation of this mutual information constraint, where the data say that you cannot push this onto one line or you can't fit the data anymore, that means that we have some resolution in the gravity data. But yes, it is much less. But for the from a mutual information perspective, it is, if you want, so beneficial. But of course, and this is a process that I'm in at the moment, we have to still carefully test sort of where in the data are different features. And I have started, for example, with these sort of replacing those with low density, and that definitely doesn't match with the observation. On the MT inversion, have you considered doing anisotropic inversion? To be honest, no. I mean, this is already, if you want to, involved enough, and I would say anisotropy adds another layer of complexity, and then you would have to think how that relates to something like density. I would say it's interesting, but for the longer term future, certainly from a joint inversion perspective. Then Jaja-san, cross-gradient joint inversion can also recover the relationship between resistivity and density. Have you tried that and compared the recorded relationship with what you obtained from mutual information? Actually, yes. So for a long time, I've actually tried something with cross gradients. And I mean, I myself have published a paper where I show that you can reconstruct property relationships from cross gradients, and some of my interest sparks from there. For the US array, I don't have the plot, but it looks very much like this. You get just a sort of unstructured blob. The gravity model here, sorry, I have the individual one up here, yes. So this gravity model gets some changes, but to be honest, for a long time, I was utterly disappointed by the cross gradient results for the US array. And I think it's because it is not quite strong enough. Yes, there's too much flexibility for the gravity to do whatever it wants still and satisfy the cross gradient constraint. So I've run many versions of that and haven't gotten anywhere near these results. Okay, the map views of resistivity and density look a bit spotty. Is any of that due to the distribution of MT stations? That is, anomalies may be stronger close to a station and weaken moving away from the stations. There is probably some of that. Now, so here at 30 kilometers, yes, there's probably some effect of that, but I think with other stations, and for example, we have a dense profile here, we also recover some of that heterogeneity. So yeah, I can't fully exclude that, for example, in some regions where we have bigger data gaps, there might be some of that going on, but overall at the depths I'm plotting here, I would say that the majority of this variability is at least somehow related to what's going on. Now, I wouldn't want to sort of interpret the exact shape of each of those heterogeneities.
Sorry, Max, if I could just jump in here with a question, seeing as if you got that slide up. The model at 30 kilometers, it looks, to me, it has the same sort of potential problems that NASA MechBells has, in that there seems to be a lot of continuity along the model axes. And I'm wondering whether you didn't talk about how you do your smoothing.
Yeah, so there's this
smoothing along model. I presume you're smoothing along grid coordinates, and so you see a lot of north-south continuity in the east and a lot of east-west continuity in the west.
There is some of that, yes. I mean, now that you mention it, certainly this here in the sort of Snake River Plain, if you can see my mouse, yes, this sort of L-shaped thing that is probably related to that. Now, there is a first order smoothing applied here. It is calculated along the axis, sort of the north-south axis lines, but it does sort of in the long term, certainly over so many operations, also operate diagonally. So there is a bit of that, but I think, I mean, I would have to do some tests, certainly, if I want to interpret, let's say, some of these strikes in more detail. I would have to check how much sensitivity I have. But yeah, I don't think it's a dominating problem. There will be some effect of that, but I don't think it has a sort of a huge impact. Okay, Johannes Kaufel, on slide 14, could you explain the ME plot more? It has two maxima over the course of the inversion, but then approaches a low value towards the end of the inversion. Okay, actually, I realized one sort of slightly imprecise thing. So I'm actually not plotting the mutual information, because mutual information, as I explained in the beginning, should increase as the more well-defined our relationship is. So I'm plotting here the, if you want, so turned into a minimization problem derived variable related to mutual information. So lower what I call mutual information here, lower values mean a better defined relationship. And what you can see basically in the beginning, yes, in order to reduce the misfit and get away from this terrible sort of 50 RMS, it introduces some structures, and the inversion doesn't really care that much about the mutual information. So it introduces some structures that are different between those different models, and that's why this term rises. Then it sort of has reached moderate misfit values, so the mutual information sort of starts to kick in and take over, and it minimizes it. And then, yeah, I didn't mention this, at this point, at around iteration 500, it just didn't progress anymore. And you can see that we are still at RMS. Okay, the scale is not great here, probably RMS 5 or 6 for the MT. And I knew from the individual inversions that this was, you know, way too high. So I actually decreased the weight of the mutual information inversion, and that allowed then the inversion to progress. So it shot up within very few iterations. The mutual information went up again, improved the misfit, and then, and this is, if you want, so basically the stage I'm in now, I'm just trying to hone in on this relationship. Okay. So that's, so the next question, will it be interesting to also incorporate teleseismics? Yes, definitely. And Bernhard Weise, who is also on the presentation as an author, he is working on surface wave inversion for this area. And yes, the long-term plan or medium-term plan is to then do surface waves, gravity, and MT, but again, it adds another layer of complexity. So for the moment, I'm quite happy with these. Okay, so Alexander Greiber, gravity measurements are fundamentally limited in recovering depth-dependent distribution of density. Yes. So it seems that a lot of depth dependency in the density recovered in the joint inversion is here because gravity gives you a lot of freedom to fit the data. Yes, that is true. From that perspective, having other variables that are actually sensitive to depth-dependent distribution, seismic velocity, should give you more physics-driven constraints. Yeah, definitely, that's true, and it's sort of related to the previous answer. So yes, a lot of the, if you want, so depth structure comes from the gravity orienting itself on the sort of MT model and sort of being happy to, if you want, so tag along. But again, I would argue that if it was sort of, if it had no depth resolution, if it was sort of completely oblivious to really what's going on there, then the mutual information constraint would push all these scattered values onto a single line. And if we have something like this backbone relationship here, everything would nicely fall on this line. So the fact that we're not getting that, and it really sort of pushes these things that annoy, if you want, so the mutual information constraint means, at least in some parts of the model, not everywhere, the gravity data does provide some new information. And I mean, to be honest, when I started this, I mean, I didn't really start this as a hypothesis test for fluids in the crust, but as a first try, that happened to work out, as I think, really nicely. And now then I discovered that I can probably tell something about these fluids. But yes, seismic velocities, seismic data in some form will be very helpful. Seda Hansen, in your plots of MT data fit, what does the color of individual apparent resistivity points represent? Good question. I didn't explain this. So the color is the misfit that I have in the inversion. So yellow here means high misfit. No color scale here. I think at around sort of 6 or 7 RMS, and then blue means low misfit. So you can see where it fits very nicely. It's all dark blue, and then where we get a bit of discrepancy, and here probably very small error bars that then hit the error floor, we get yellow colors. An anonymous question: optimization, joint inversion, magnetotelluric, and gravity data. Okay, I think whoever wrote this I don't understand the question in here, so that needs to be sort of rewritten. Emmanuel Njiju, comparing the quality of the MT data versus the gravity data, which do you think has a dominant effect in the results? So yeah, the MT, I think talked about it a couple of times. The MT data certainly brings more to the table than the gravity, but the gravity makes some modifications to the MT model compared to the individual inversions. But as Alex Guyver and others said, the depth dependency or depth resolution is relatively poor. So that's all or mostly driven by the MT. Okay. Sergio Espinosa, I have two questions. Why do you use the word mutual information instead of correlation? It is clear to me that correlation does not necessarily mean causation. So it's two different quantities, yes? I don't calculate a correlation coefficient. I calculate this mutual information quantity. If you want to think, or if you want, you can think about mutual information, slightly simplified, as an extension of correlation to nonlinear processes. Yes, if you have something like y equal x squared, and you calculate the correlation between sort of data derived from this equation, you will get a correlation of 0 if you cross the 0 axis into negative x values, but your mutual information will be high. And yeah, correlation does not necessarily mean causation. No, of course, it doesn't. If you want, so it's another way to think about it. It's a hypothesis test. Can we invert these data and construct some sort of relationship between them? And the answer is we cannot refute the hypothesis that these data can be inverted with some sort of relationship between them. Now, what that means, that's sort of up to us to interpret. And then second question, I have the gut feeling that mass density at 100 kilometers depth from satellite gravity measurement does not have the same resolution as electrical conductivity at 100 kilometers depth from MT measurements. How do you reconcile disparate resolution differences? On top of this, conductivity is influenced by anisotropy, while density is not. Yeah, no, definitely both are true. Well, we've talked about the depth resolution of gravity data sort of a couple of times now. And I mean, so far I haven't tried to interpret the results at 100 kilometers. And there, for example, if you look here, you see a sort of a very good correspondence. So certainly the theory that a lot of this density picture here is just caused by taking the resistivity model and sort of applying the relationship and making a density model out of it holds. On the other hand, and that's one thing I've looked at. If you look here at around minus 110, 41 degrees, there's the structure here that is highly resistive but dense, whereas everywhere else highly resistive and light, whereas everywhere else highly resistive means dense. So again, the inversion did something there that contradicts the mutual information constraint. So there has to be something in the data that wants this feature there. In fact, this is another interesting region, but I'm not going to sort of go into that. That would probably lead us too far down another route. But I can talk about this privately. Feng Jiang. Hi, Max. And most of time, the resistivity values from MT inversion model will change with different inversion parameters, such as different initial models. How will we consider that we can calculate the content of partial melting from resistivity model? Can joint inversion help to constrain the absolute resistivity more accurate? Not really. I mean, I am running at the moment as part of the tests I'm doing another joint inversion with a 1,000 ohmmeter starting model. But if you want, so the mutual information, yes, if I need to go down to this relationship. So if I shift this whole thing up or down, Yes, because I start, let's say my MT doesn't have any absolute resistivity, sensitivity, I'm inverting phase tensors or something. If I shift this whole thing up or down, it doesn't change the mutual information. So this won't help me, even if I have, you know, something like seismic data that has great sort of depth resolution. So the only thing I can hope for is that maybe because some structures then are pushed up or down in the model, the resistivity will be fixed. But if I use, or if I think that my MT has problems with the absolute sort of background sensitivity, resistivity, then the joint inversion will not really fix that. Okay, I'll skip the next anonymous one because that's again just a sort of a bunch of words. Chao Jian Chen. Any more information is obtained by a joint inversion of MT and gravity data sets, especially for the deep structure. If checking the single inversion gravity data, the resolution of deep structure is low. Yes, but yeah, I mean, and this has been brought up by others, yes, you have to be a bit careful that you're not just interpreting something where you have, you know, if you have no resolution for the gravity data, but your density model looks like that, of course, you could argue that this is all just fantasy, yes? So, and this will be part of the testing to make sure that what I'm talking about now will have, you know, some impact of the data. If I can change, for example, what I talked about now, this low density structure here to high density without impacting the data, it means, okay, this picture looks nice, but I haven't actually gained anything. So yes, potentially, especially if it's sort of slightly subtle, but you have to be careful. Okay. Susan van der Lee, one place where fluids are 100% expected is in a subduction zone. Yet that's where your last slide did not show a correlation between density and resistivity, similar to cratons. Why might that be? Okay, yes, we would expect fluids in a subduction zone. Okay. So you are talking about sort of the western part here. Now, can okay, I should have prepared this slide. We do have some MT sites here, but I mean, all the models that we have don't really show a lot of sort of conductors here in this subduction zone area. Yes. So if you're talking about here where we have the slab, for example, but of course some of that will also be off the coast. And this is also true for, if you want, so the other published models. I mean, you can see, or you could argue that here we see sort of a little bit of a conductivity, and that's probably shallower. So this is 30 kilometers depth. So here the fluids would be also shallower. But yeah, this is a feature of all the models. So I'm not 100% sure, but certainly from the data, it doesn't seem to require like a highly conductive structure there.
If I could just jump in, Max.
Yeah, sure.
If you go up to Vancouver Island, because the rocks are much more resistive there, the anomalous response due to fluids given off the plate is about 15 degrees in phase. This is from the old Kurtz work. It's a big anomaly. It's easy to see, but at the EMSLab line, which is the line in Central Oregon, the anomalous phase difference due to fluids coming off the plate is about 2 degrees. And because there's a lot of conductive structures around, and so you really have to focus in detail on this very small phase difference of just 2 degrees. And I think it would need a much more focused study in that area in order to make sure that you're fitting those anomalous data to that level. Whereas what you've got is a global misfit. You're fitting the whole of Western US. And so if you really want to look at the fluids off the plate, I would suggest that you really have to look at the sites that are on top of the subduction zone. And that would then fit to that level, to sub 2 degree level.
Yeah, and of course, in a way that also relates to some of the things that were sort of asked before. Yes, the site spacing here is sort of on the order of 50 to 70 kilometers, and you know, it's really not sort of tuned to that sort of, if you want to, smaller scale, those smaller scale structures. Okay, next question. Wolfgang Sawyer. How do the model densities compare to gravity data on a map? Possibly an interesting test could be to apply the method on a random gravity data and compare density results in cross plots. So it does look different. I have plots of the MT data, not of the gravity data. Actually, if you want, so the individual density inversions, they just look like you take the gravity data and apply a different color scale and then sort of plot them. So there we really get, if you want, so a one-to-one relationship between sort of a gravity measurements on top of a certain area and the density below. Here it becomes much more complex, and we can see also the strong influence of the conductivity model. And the second part, so I assume you mean take my MT model and then generate some, if you want, so bogus gravity data, just some random stuff, and see if I get something back that actually looks meaningful. So sort of testing if I'm looking at something that sort of evolves in any case, regardless of whether there's meaning to it now. That's actually a very good idea. It's very interesting. I will try that. I guess depending on how extreme you do it, I would think that you can distinguish between those cases. But that's a very good idea, and I'll experiment with that. Just taking some sort of either extremely noisy data, or even sort of completely random data, and see if the joint inversion suggests that there is some relationship there that actually shouldn't exist. Phil Wanamaker. Density of lower crust depends a lot on silica content, granite versus gabbro. Snake River Plain has received a lot of mafic underplating and replacement, implying the high density, but residual fluids melt can still make it conductive. Okay, I assume this is the thought that, okay, what you're seeing here with your high density areas is not actually if you want, so the conductive medium, but a change in the density of the host. I think that's what you're saying here, Phil, and that was one of my first thoughts. Now, my argument against this was, if that were the case, yes, we would expect to see, if you want, so something similar to this, but somewhere over here, yes? Because what we would have then, we would have a host density that's maybe plus 100 kilograms per cubic meter. We then put fluid in that, so we still have a density contrast. So increasing the conductivity would then require us, even with a sort of stronger slope than this, to decrease the density. Yes. So if you want, so if I can talk about this dinosaur thing again, this front leg then would be sort of bent towards the back. This is my, if you want, so justification, argumentation, why I don't think it's simply a change in density of the host rock, but instead we see sort of constant density, but change in resistivity. So to me, that suggests that whatever causes that conductivity has at least a similar density to the host rock. Williams Lima, just an idea, maybe the cosine similarity could have better convergence behavior than ME, still giving similar results. I'm not 100% sure about the cosine similarity. I think there's the one thing I know that sort of a bit related to this is very similar to the cross gradient. So if it's that, I would say it probably behaves like the cross gradient. If not, I will certainly look into it and find out what it is and if it can be used. So if you want some reference, and would be nice to either email me or put it in the chat. In MT RMS plot, could you explain what you did to the inversion between iterations 1000 to 500 to 2000 and how did it affect the data? So I did two things. I think I mentioned this very briefly. I assume you're talking about this here. So before, so this here up to here, I used a row-wise error floor. So the diagonal elements would have relatively large errors. So for example, XY, and this is XX, the error floor for those two elements would be computed together. And because we can see here, for example, XX is much smaller than XY, these diagonal elements would have significantly bigger errors. At this point, because I wanted, as I said, the best possible fit, I changed this and I used individual error floors for the diagonal and off-diagonal elements, and I also doubled the amount of frequencies. But I think that actually the main impact here, the change in frequencies didn't actually do very much in terms of the RMS, but the main impact here is this change of error, just to push it as far as I could. Seda Hansen. In the resistivity model from Tibet, there were a series of subparallel conductors. Do you think that this could be an artifact caused by anisotropy? If so, could gravity map of the area provide a first comparison to help interpret how accurate the geometry might be? I mean, I've never worked in the area, so all of this has to be taken with a lot of caution. But yes, these sort of conductive, resistive, some people in other regions, and maybe even in Tibet, I'm not sure, have interpreted things like that as anisotropy. Yes, gravity data, again, if you have enough resolution, could be used to test the hypothesis whether you can create a gravity model that shows, if you want, so similar stripes, or if this is really intrinsic anisotropy and everything is homogeneous in this area, then you would see a different gravity response. I think I'll leave it at that because
just, Max, if you don't mind, a lot of those north-south features in the Lhasa block, they actually correlate with known extensional grabens. You have in the southern half of Tibet, you have east-west extension giving you north-south grabens, and we can see that when we go in more detail, that those conductors there we can relate to these extensional grabens.
Okay, yeah, as I said, I know relatively little about this area, so yeah, that's of course also so Makoy Didas, is the joint inversion presented 1D, 2D, or 3D? So it's all full 3D. Do you think including the topography in your model would improve your results? So for the gravity data, we've done a complete Bouguer correction. So all the topography should be removed from the gravity data. On this scale and with the topography of this area, I would think that the impact on the MT results is, let's say, relatively small. I haven't talked about this. We use also the distortion correction that we've published for just MT in the joint inversion. So that should take care of most of those topographic effects, certainly at these sort of long period data. But of course, in general, certainly if you want to reduce the scale, then taking into account topography will be useful, or in some cases even necessary. Then we have Last question, Abbas Fanai. What do you think about the results on the joint inversion of empty and ground gravity survey data? Yes, this, I assume, can this applied in the same way? Yes, there's no real difference between ground and satellite data. It's simply different how it's been acquired, and obviously you need to take care of things like I just mentioned, having the right corrections, boogie correction, and height correction, that you can incorporate that. But other than that, you can use the same method on ground data. Is there a clear pattern between resistivity and density changes? Well, that's to me, yes, that's this comparison. Yes, and I think yes, you can say definitely yes. We see quite clear correspondence between different structures, or if I swap back between those, you can see that in large parts of the model it more or less looks like I'm simply changing the color scale, and there are just a few areas like here in the Snake River where this looks different. So there, I think yes, there is a clear association. Well, also shown by the parameter relationship. Okay, one more question has just come up. When you minimize functionals, do you use weighting? Yes. So I haven't talked about this. This would go too far. So here, and as I said, there are sort of also regularization functionals involved here, and each of those has a weight. And certainly in the inversions I've run, these two have been weighted sort of the same, so just one, but I've varied this. I've talked about this a little bit, and I've experimented with different smoothing. So I've done different runs with different weights, and that's sort of an important part, of course, of performing a joint inversion, understanding what the impact of these different weights is.
If I could jump in and ask the last question, Max.
Sure.
Or maybe make a point. If you can bring up your dinosaur plot.
Yeah.
I thought you were a little bit dismissive about sulfides.
Okay.
One of the largest conductivity anomalies in the world, the North American Central Plains conductivity anomaly, we can relate to sulfides because we got exposure in the northern end, and we can track it for 3,000 kilometers. Now, on that plot, sulfides would lie, because they're high density, very low conductivity, sulfide grains would lie below the plot on the high density, very low resistivity space, right? Yeah. But of course, you don't have grains. You've got 5% of sulfide. So I'm just wondering whether, in fact, that an explanation for that front leg might, in fact, be sulfides. But of course, you can only use that really in the crust, and I see that some of that front leg is quite deep.
Yes. Yeah, two things. Definitely. I mean, as I said, I think in the beginning, the sulfides, that's my personal impression from some of the papers I've read, that they were sort of a bit sulfides have been mentioned, but not probably not so much. That's something I definitely have to look into, and I don't think I can distinguish that. And then with the depth dependency, yes, there are some deeper things here. Now, of course, if you want to, once this develops, for example, because in the crust it is needed by the data to have such a front leg, then other parts of the model, yes, might sort of opportunistically decide, okay, if I need to make some sort of connection there, I might as well sort of move onto this leg instead of having another scattered point, because all these scattered points, they reduce the mutual information. So that would need some testing, whether, for example, this really deep stuff here is required by the data. So, I mean, those are still things I need to do to really sort of unravel some of those different effects from each other. So, yeah, sulfides are definitely a possibility. I didn't want to be too dismissive about them.
Let's finish off by thanking Max again. It's been a very exciting talk, and kept the audience for an hour and a half. If I can get the screen back now,
Sure.
just to remind everybody that next week's EMinar is by Karen Whitemeyer, and it'll be a couple of hours later, so 1600 UT. And thank you everybody for attending, and I hope to see you in a week's time. Bye for now.
Thank you very much.